Okay, if we can start on page 8. Okay, so today we're starting on page 8, and I like to do things a little differently. At the end of class, I like to just check whatever we've done by the end of class, and that way I don't have to check homework tomorrow because I like to just start with a new section tomorrow. Okay, so let me check the classwork. So no homework today, but we'll just check classwork at the end of class today. And it'll just be from page 8 till wherever we end up at the end of class. Okay.
Yeah. I am still after my son. Thanks for checking on it. I'm feeling better. My side is good.
Okay. Okay. Page 8.
But then he just put it.
Any questions with page 7 that you need me to go over with you? Okay, so the graph shows polar curve r equals 3 minus theta from 0 to pi. What is the area of the region bounded? So they're already telling you where the region is. So, but we can create a table of values just to see where we are. So if we start at 0, 3 minus 0 is going to be 3. And it's going to move in the clockwise direction. If we plug in pi, we'll get 3 minus pi, which is almost at 0. So that's why it looks like it's a little bit off. But essentially, anytime we're involving area, we're always extending our regions from polar 0 and extend it out to the curve. Okay, the rest can be plugged in the calculator. And again, I like to just do it in function form. No need to do this in polar form. No need to involve theta. Just use x in your calculator. But we do want to make sure that we're in radian mode. Okay, at time t equals 0, between 0 and 2 pi, the position of the particle is given by a vector value function. Find the slope of the path. So we have our x component, we have our y component. We can just find y prime over x prime and plug in pi over 4. Any questions with 15? All right, find equation for the line tangent to the curve given by the parametric equation. So we can plug 2 in for x, plug 2 in for y, get the order pair, create our slope, which is y prime over x prime. Replace all the t's with 2, get our numeric slope value, and then finally end with point slope form. Okay, any questions with 16? Okay, before we do number 17, let me just review a little bit with reference angles. You guys probably know this already, but just wanted to just do a quick review here. Let's say we had cosine of theta is equal to 1/2, right? What would you say theta is equal to? Where's cosine equal to 1/2? And 5 pi over 3. Now these are all special angles, so we kind of have this memorized already. But I just want to point out that this pi over 3 is the reference angle. And we know that cosine is positive in the first and fourth quadrant. So the reason that we're able to get to that 5 pi over 3 is because we are taking that pi over 3 and we're subtracting it from 2 pi to get to that reference angle in the fourth quadrant, right? So 2 pi minus pi over 3 ends up giving us 5 pi over 3. If it was something that we need from the second or third quadrant, we would either add or subtract from pi to get into that second or third quadrant, right? So once we find that reference angle, we can always either add or subtract from pi to get to that second or third quadrant, or we subtract from 2 pi to get to that fourth quadrant. Okay. Now, this is right now it's kind of obvious because we're dealing with these special angles or these unit circle values. But if we're not dealing with unit circle values, we still have the same thing. If this is a decimal value in radians, we would subtract 2 pi minus that radian to get that fourth quadrant. But if we want to get to the second or third quadrant, then we have to add or subtract that decimal value from pi. Okay, so that's the, just want to point that out as we move into 17, where we may be dealing with radian measures that are not unit circle values, but we can still use this knowledge to get into the quadrant that we want to get to. Okay, so find the total area enclosed by the inner loop. So anytime we're dealing with inner loop, we know that we're looking for polar zeros. Because polar zeros is what's going to close off those loops. Okay, so to find polar zero, we're going to set our equation equal to 0. Okay, so now this is something that we don't recognize, right? Sine of theta equals 4/5. This is not going to be a unit circle value. It's not like 1/2 or √3/2 or √2/2. So this is going to be a decimal value that's not going to land on one of these special angles. But we can still solve for theta by using our calculator. And whatever we get is going to be a reference angle in the first quadrant. And I got 0.927. Where else is sine going to be positive? Second quadrant, right? So the way we get the second quadrant is we identify that reference angle. And then we subtract from pi. Just like if it was pi over 3, we would subtract from pi and we would get 2 pi over 3, right? Because pi minus 2 pi over 3 is 2 pi over 3. So same thing, it's just that now we're going to lean on these decimal values because we know it's not going to be a unit circle value. So theta is also pi minus 0.927. Which is 2.214. And now these are the theta values that we're going to need for our interval bounds. If I want to find a third quadrant variation of that 0.927, then I'll just add pi to this. If I want to find a fourth quadrant of this 0.927, I'll subtract 2 pi minus that. So whatever first quadrant value you get, you can always get to the corresponding second, third, or fourth quadrant, either by adding, subtracting pi to get to second, third quadrant, or subtracting from 2 pi to get to fourth quadrant. So having done this, can we go back to page 6 and try number 6 now that we see this is kind of the path we're going to involve if we're dealing with these non-unit circle values? Any questions here? So yeah, let's look at this is the problem that we skipped yesterday. So this is page 6, number 6. A polar curve is given. What angle theta corresponds to a curve with y coordinates of -1? So we know that y is equal to r sine theta. So that's our connection between polar and rectangular. Okay, replace r with what is provided. And then replace y with -1 and see if we can solve for theta. Cross multiply so I can just get the fraction out of the way. Okay, so if we want to solve for theta, we see that we don't recognize that -3/4, right? This is going to be a non-unit circle value, but we can still use our calculator, use inverse sine to plug in. And I got theta equals -0.848. Now, if we just think about the positive value, that 0.848 is the reference angle, basically. And then we can make this fit wherever quadrant we want it to fit. Where is sine going to be negative? Which quadrants? Yeah, third and fourth, right? So I want to find the corresponding measures in the third and fourth quadrants, knowing that 0.848 is our reference angle. So if I want to get to these third and fourth quadrants, I can subtract from 2 pi. And then I can add pi to 0.848 to get those values, right? So pi plus 0.848 will get me that corresponding third quadrant, 2 minus 0.848, right? Just like if these were special angles, if this was pi over 4, you would do 2 pi minus pi over 4 to get to that fourth quadrant angle, pi plus pi over 4 to give that third quadrant measure. Okay, so 0.848 plus pi will get into third quadrant, which is 3.99. Fourth quadrant, 2 pi minus 8.848. Fourth quadrant, 5.4. Okay, page 9. Okay, what is the slope of the tangent line to the curve defined parametrically? So find your x prime, find your y prime. Divide them by each other. Get your slope. But there's some additional steps we got to take because we don't know what the t-value is, but we can plug the 2 and 3 in for x and y to find that matching t-value where x and y are hitting 2 and 3 at the same moment. So the additional step that we need to take is we don't have the t-values, so we're going to have to plug 2 and 3, see if we can find a t-value that is matching when x and y are both hitting 2, 3 at the same time. So we find a consistent time when the graph is hitting that 2, 3 at the same moment. So if we plug 2 in for x and we solve for t, we get t equals 4. If we replace y with 3 and solve for t, we also get t equals 4. And so we know t equals 4 is the moment in time that we're evolving to find the slope. So find your x prime going through power rule, y prime also power rule, and then y prime over x prime, and then replacing the t with 4. All right, number 2, second derivative. So treat this like parametric. Find your x prime, find your y prime, find dy dx. And then there's the formula for second derivative where you're finding the derivative of dy dx, but then making sure that you still remember to divide that whole expression by dx d theta. Number three, we're just applying parametric arc length formula. So find x prime, find y prime, and just fit it into that arc length formula. Okay, number four, the position of the particle is defined by a vector value function for what value is the particle at rest. So that means we're going to set both the horizontal and the vertical components of our velocity equal to 0 after we find our f prime. And we're trying to find a matching pair of time when both the x and the y are not moving. Because if x is moving and y is not moving, then it's not quite at rest. So at rest would mean no horizontal motion and vertical motion at the same moment. So we're going to set both x prime and y prime equal to 0 and see when they're going to agree at a time when both velocity is 0. So it could be completely at rest. Okay, so set v of t equal to 0 for both your vertical and your horizontal components, both your x prime and your y prime. All right, page 10. Find the slope of the path of the particle given your vector value function. So find x prime, find y prime. You're going to need product rule for both x and y prime. And then we just find dy over dx at the end, replacing all the p's with pi over 2. And so right now we're have a vector function that's at the position level. We want to get to the velocity level. So let's find f prime. So x and y component, find x prime, find y prime. Replace all the t values with pi over 2, and then you can do y prime over x prime to get your slope. All right, number 6, we have velocity vector provided. We have also a given point provided as well. So it wants to know how far the particle is going to end up from the origin at time t equals 1. So let's figure out the location at t equals 1. So let's use a particle motion formula to locate the object's horizontal location as well as the vertical location. So we're going to use final equals initial plus displacement, once for the x component, once for the y component. And once I can find that final order pair, I can just compare that distance with 0, 0 to figure out the distance from the origin. We know that at t equals 0, the object is going to begin at x value of 1. So we have to figure out how much distance this particle has traveled horizontally between 0 and 1. So we can just go through the displacement formula to figure out how much he actually travels. So we know that he starts off at x equals 1. He's going to move 2 units to the right, and so he's going to end up with an x value of 3. Okay, apply the same process for the horizontal, for the vertical motion. This one we can just plug in the calculator, 2 to the negative t squared. That's the integral. So we know that this particle is going to end up at order pair 1.31. So think of it as you're just finding that distance. Think of it as finding your hypotenuse or your right triangle. A squared plus b squared equals distance squared. Take the square root. Sorry, 3, not 3, 1.2. Same formula for number 8. We're just doing a horizontal component. Sorry, for number 7 is total distance, which is same thing as arc length. Number 8 is similar to number 6. Just number 8 is just asking for the horizontal x coordinate of the position. Okay, just flip through. Let me just see your pages 8 through 10. 8 through 4 through 7. Most of them will finish here.
It's like you always.
Yeah, I just like.
Morning. I didn't see you. I actually, you should always on me about missing. I'm trying to be. You see physics, see background. That's. Like, so it's my favorite. That's good. I got it. But yeah, I guess now. Memphis first. You can have a stand. Yeah. I have all the power in my hand. Like I have I'm gonna take 7. I'll break you. That's what I'm saying. Like I take it tomorrow. So like I have all the power in my hand. If I do that,